Thank you. Mic check, 1, 2. All right. Hello. I'm Markku-Juhani Saarinen. I'm with PQCrypto and Tampere. So, outline of the talk. So first I'll go through the problem statement a little bit, like explaining why this is an issue, especially with side-channel secure hardware implementations, why key management isn't like a special problem in that case. Then I'll try to focus on the little trick that is really at the core of WrapQ. I think I'll try to focus on that to try to get that message across. And afterwards, we have the necessary things about leakage assessment and implementation details about this to show that it's practical and that it's a component that we actually use in hardware implementations. So one thing about side-channel attacks is that if we focus on dilithium and Kyber specifically, they basically inherit all of the side-channel requirements that we now have for RSA and elliptic curve modules. So in these hardware implementations. So this is of course in like secure boot, firmware updates, attestation, authentication token, smart cards, HSMs, these sort of small implementations where the focus is, or the added value of hardware is not speed, but specifically security. So this is the sort of branch of hardware security where it's really about side-channel security and not much else. And it's of course a market requirement. So if we want to sell a hardware module to be used in specific markets like smart cards and so forth, it needs to be certified at a fairly high level. And it's kind of surprising that common criteria, for example, which is used in these markets, can be adapted to post-quantum crypto fairly easily. So there's things like the AVAVAN, Advanced Vulnerability Analysis, which is a methodology that these certification labs use. It seems that it can be adapted to post-quantum crypto. So we basically inherit all of these, I don't know, 20, 30 years of requirements on various fairly advanced attacks. So that's why we are doing it. Now, for these lattice-based schemes, the main sort of countermeasure that is applicable is based on masking. So masking is sort of like secret sharing, where every secret variable is split into several variables which individually look random. You can get all of them except one, and you should still not know the secret. So that's kind of, from a side-channel perspective, that creates noise because everything, all of the data being processed, it looks random, so you can't get the signal out and so forth. Nice thing about this, sort of from a theoretical viewpoint, is that the attack complexity in certain statistical or information theoretic even viewpoint of it is that grows exponentially with the number of shares that we have. And this is of course why we want from a countermeasure. We have a polynomial time countermeasure and which makes the attack exponentially harder. But of course that would be the case only on very high order implementations of these things. And typically in actual hardware we are limited to only first or second order. So that's another thing. Anyway, so the way these masking countermeasures are applied is that because we have to decompose all of the arithmetic into these little every little step that we have in the pseudocode, which is dealing with secret variables, we need to decompose it so that the actual secret variable is not visible. So we are computing on shares. At no point are we allowed to sort of collapse secrets into the actual value. So that's why we decompose them into these little gadgets. We invent methods of doing all of the arithmetic steps, and the basic steps, NTT, a little bit bigger steps, and build the algorithm that way. Now, what's needed there is that we are always refreshing. All of the proofs basically collapse or don't work unless we are refreshing the sharing all the time. So you are simply not allowed to use the same masking, the same split of the secret multiple times over, because if you do, it's equivalent to not having masking. So the proofs really require refreshing. So there's a couple of models that these proofs are made. So one is deep-probing security, which is the typical way of proving things. It's a very kind of simple way of approaching it. Then there's some little bit more realistic models like the noisy leakage model and so forth. Now this is the problem statement that we have in here. So your secret key looks now completely different. You can't use the normal format secret key even temporarily. That's plain text. So if you have a masked secret key, it needs to be masked really all the time. So this affects like the hardware architectures that we use in high assurance. So for example, in high assurance, TLS handshake would have a masked key declaration, masked HKDF, passing masked AES keys and masked authentication keys around. Everything is masked, if you want to go that way. And another thing is that typically a cryptographic API, just has a key somewhere and it loads it up and uses it. We can't use that because it needs to be refreshed every time. So a masked implementation of a signature scheme, basically every time you sign, you need to write back a refreshed version of the secret key. So the APIs don't really allow you to do that. Quite often a key can be in ROM and it's simply impossible to write back or refresh that secret. This is, by the way, this is often ignored in academic literature. The key simply exists and then you start a dilithium private key operation. So where does the key come from? Where is it stored? So that's really the issue here. Loading a key, making it available for use is almost always the sort of step 0 of a private key operation. Of course, it needs to come from somewhere. You can't just generate it there because it's a long-term key. Now, another issue is that the keys are kind of bigger. So a typical hardware key management unit has these slots which are big enough to hold an elliptic curve secret key or AES key, like 256 bits in shares or 512 bits in shares, but these are massively bigger than we have. So we have a way of addressing number 2, the refresh, and the largeness of thing, but unfortunately we can't use the standard key format. So when we store secret keys and use them in a mask implementation, what we can do is just have the plain old, the format used in cat test vectors and just expand that into masks and start using it as a mask key. Because that step where you are exploding this static key into masks would just leak the secret key. So we can't really do that in good and say that it's secure. And it would also, it's funny in sort of t-test, TVLA, they sometimes say that this is not an area of interest. So they specifically scope out the hard part of the key management, which is funny. Scott is nodding. All right, so the little trick that we have here. So first a little technical thing, or an observation, is that if we have shares, then we can't collapse them into a single share at any point. But if it's ciphertext, then that's fine. It's kind of interesting. If it's encrypted, if we are processing encrypted information, then it's secure by the virtue of being encrypted. So in order to make the secret key smaller in storage, we kind of have to encrypt it anyway. Encryption helps us to remove basically a first-order masking would otherwise double basically the secret key size. But it's fine, we can reuse it if it's ciphertext, and we can somehow decrypt the ciphertext directly into these shares. And this decryption process needs to explode basically the ciphertext into different representations of the secret key every time. So we have multiple shares, so that means that we can sort of always create a different representation on the fly. But the trick to do this is actually surprisingly simple, because to build a masked version of either Kyber and dilithium, we need a masked version of Shake anyway, because internally these algorithms process secret data. They do hashing on secret data where both the input and the output are are actually masked. So we have this magical primitive that takes in masked information. We have a Ketchak permutation and then spits out a randomized hash. It's standard compliant. If we collapse each one of these masked representations, it's still shake. It's a Ketchak permutation. But so the basic trick here is that if we run that Ketchak in counter mode, we have a magical masked stream cipher, which produces key stream in shares, which we can use to decrypt a ciphertext directly into this, always a different representation of the secret. This is really the basic trick. It's kind of, there's an anecdote to this. So, for example, mask implementations of AES, funnily enough, they don't focus on protecting the plain text. You know, one would think that the whole point of having a secure implementation of AES is to protect the plain text, but no, they are almost always protecting actually the secret key, which is just a method of protecting the plain text. So quite often the mask implementations of AES, because of this worst case scenario where the attacker can control the plain text and do a known plain text or known ciphertext attack, they actually assume that it's always just known. So AES implementations are, or masked AES implementations are kind of rather difficult to use here. So, but we have this very expensive component. By the way, it's very big. It's 100,000 gates in ASIC to have a masked Ketchak. But because we have it there, we are going to use it also for this purpose. So in concrete terms, here's an example. I guess this is the most informative slide about the core trick that we have in here. So we have the XOF, the extensive, or that's the Ketchak permutation. So this is the standard Ketchak permutation with the exception that it takes 3 shares of the input and spits out 3 shares of the output. So if you XOR inputs together is a regular input. If you XOR the outputs together is the expected output. But the output is every time different. It's a different representation of the same X. Now, in order to decrypt, we have a ciphertext block. You know, it's just one block. We first randomize it, just in case, into 3 shares. So that's different every time. We can do that because it's still ciphertext. And only after that, we just XOR our masked key stream on it, and we have 3 shares of plain text. And that's actually the secret key for the asymmetric component. So that is the core trick here. Now, encryption is when we are wrapping a secret key. We are turning let's say, a key we just generated into a wrap format. It's a stream cipher, so it's very similar. So encryption is basically the same as decryption, with different arrangement of the refresh gadgets. Now, the way we are addressing the fact that these are much, much longer keys is that by the virtue of wrapping, we can just store them in untrusted storage. But in order to do that, confidentiality, of course, isn't enough. We need integrity as well. So we have a key encryption key KEK in our little, basically our hardware secure storage. And with that, we can load up the key from unsecured, like let's say ROM, which is available for reverse engineering. Have the secret key decrypted and also authenticated. It has an authentication tag and so forth. The only little trick that we have here is that we are authenticating, of course, the ciphertext. So that means that we can use an unsecure hash function to process that a little bit faster, and then invoke the secret key, which is in masks only with a single iteration of the masked Ketchak permutation. So that's the only trick in there. But that will authenticate it in a side channel manner, so not leaking the authentication key in the process. Now, for this, we needed a little bit different key format, which is roughly the same size as the original one. But of course, for that, one needs to do a sensitivity analysis. This is side channel security, so we need to classify things into PSPs and CSPs. So CSP has the difference that it also requires confidentiality. PSP only requires authentication. So the red things in, let's say, dilithium are K, which is actually only used for deterministic signing. So we don't really do deterministic signing in side channel secure mode. But of course, the S1 and S2 vectors, which is the lattice secret. So those are the things that we are actually protecting in a mask fashion. The other ones, PSPs in this key format, are just authenticated. Now, so this is the WrapQ format. It's almost the same thing, slight differences in there. We are even having the same redundant things like a hash of the public key in there and some other things. Very similar situation with Kyber. We have an S, and we have this Fuyusaki-Okamoto rejection secret, which are the only CSPs in here. The rest is just authenticated, and we have a format for them here. Now, the nice thing about this is that because it's ciphertext, we don't need to multiply the size, is that the WrapQ format is not much larger. In fact, for Kyber, it's a lot smaller, and there's two reasons for that. So first of all, the normal format of the secret key contains the entire public key. We don't really need to do that in this setting. Well, it's such rules. But what this format has for Kyber is just a hash of the public key, so we can authenticate the public key. So basically, the API is being fed the public key at the same time as the secret key, so it can check that the public key is correct. And also, the standard format for Kyber uses this number theoretic transform domain for the secret key, which means that it has to be 12 bits per coefficient. But if you actually don't use that, then it can be smaller because the coefficients are smaller in the secret key. Now, coming to the implementation stuff, yeah. So this is a version of a commercial implementation that we have running on FPGA. It's actually being passed through the same process and validated the same way as the private key operations themselves and key generation and everything else that these things do. So on a very high level, it has a little CPU there. It has a lattice accelerator specifically for this arithmetic. It has a masked random number generator. So this is a component that's kind of new, didn't exist before post-quantum hardware implementations. It has in this particular case, importantly, a tree-share threshold implementation of the Ketchuk. So that's a pretty big component. Yeah, like I said, 100,000 gates. So that's the size of like 3 very small processors. But we still think that we need it for performance here. So that is probably the biggest hardware component in a side channel secure Kyber and dilithium implementation. And on top of that, it also has a faster Ketchuk permutation, and that's used to expand the A matrix and some other things in there. So that's also used here to authenticate things a little bit faster than the mask version can do. And of course, if one doesn't need side channel security, one doesn't need to use it. So here we are. So yeah, it's tested like anything else. So this is what the lab looked like a year ago when this was being done. So it's just a bunch of FPGA boards and oscilloscopes running it. The technical details are here. Yeah, so it's just a DPA thing. One generally assumes that the same kind of countermeasures would apply for DEMA. So yeah, it's running here at 50 megahertz, but on customer ASIC, it's faster. I think it's typically 500 megahertz on there. Right. So this is a little bit interesting. Like, how do we test that? So it's a little bit non-obvious because these t-tests are usually done in symmetric crypto, where it's easy. You know what the secret key is here. So we have a bunch of little tests where we just choose which variables we fix and which are randomized So these are fixed versus random tests. So this is a statistical test that basically shows if there's some leakage from this difference between the fixed key and the randomized key. If there's some statistical difference between these traces, then it should show. So there's like 8 tests that we just added to the battery of t-tests specifically for key import and export. Because our key, well, it's a little bit more important for Kyber, but also the dilithium key generation is masked, so that's why we have key export here. Yeah, so that's what it looks like, 100,000 traces well within the critical bounds. Same with dilithium. So yeah, I mean, it has all of the variants of both of these algorithms. Now, so recap. So remember, so you can't use the regular API or key derivation if you are protecting these algorithms. You just, that you will leak there. Even if you're not testing that, the attacker doesn't care and will just pick up your secret key from the key derivation. And another thing is that unless you have specialized hardware components, this sort of write back of the masked secret every time is kind of complicated. And one more thing is that you kind of need to have wrapping in a system design because the keys are just bigger. You want to have the option where you are storing the keys somewhere a little bit cheaper and a little bit less secure than the wrapped keys rather than the KEK, which is the actual unwrapping key, can then be somewhere deeply hidden. It can be a hardware intrinsic secret. It can be something very cleverly derived so that the attacker can get at it. Now, the observation is that you don't have to have such a large storage requirement if you have it encrypted. So the encryption actually helps with the size. And there's a way, like I was talking about, how to decrypt directly into shares so that the shares are randomized every time. Yes. Now, and of course, I have my proof of concept here, which I'm using. Yes, so that concludes my talk. So.
Quick question. I noticed that you were using ASCON for generation of fresh randoms. What was the rationale for choosing ASCON versus smaller footprint stream ciphers such as Trivium or something like that?
It's a total overkill. It's true, and we don't mix randomness. I mean, there's of course you need to use a standard RBG, like NIST-compliant RBG with a proper entropy source for the actual secret key generation and all of that. So ASCON is just a masking random number generator. But it's reasonably fast, so depending on how many rounds you spend on it, it will give you 64 bits every 4 cycles or 6 cycles. And that was just fit into the pipeline nicely, so it's able to like write data from there. We also designed it in a way that it can run in this sort of continuous loop where you can feed entropy from like a ring oscillator continuously. It's just a noise generator. But yeah, we would pass the same test with like LFSR even,
Yeah, thanks for the talk. You said that in the side channel secure setting, you usually use the randomized dilithium. Can you maybe explain a bit more why?
Yes, so how would I say? I mean, if you have a deterministic signature, then it's doing the same thing every time. So you have like kind of more signal to pick up there. If the scheme has this option of randomizing by itself, then that saves on the masking effort. So all of the countermeasures, like for elliptic curves, for example, the randomization of the z coordinate or the base point or everything is randomizing. So if the algorithm itself gives you an option of randomizing something, why not use it? I think it's like, I don't know. It's just, this translates also to performance. Of course, we can deal with the with the deterministic version, but it will be slower. So there's that.
Okay, your second point up on is that the secret key write back is a bit tricky. Can you expand on that if you don't mind?
Yeah, so it's, well, I mean, it's on one level, it's an API issue that, you know, in like C, it's a vector where you can't just write back the where it's loaded from. And keys are quite often in places like ROM, or they might be fixed. So it's just that we can't just modify them back. So and there might be some like technical issues with like synchronization. Someone might like play with our power supply while we are writing back and corrupt it. And you know, it just feels better if we can just have it statically somewhere and load it.
Okay, thank you.
Okay, so let's thank the speaker again. Oh, sorry, no, there is an extra question. My bad.
Just one more question. Thank you very much for the presentation. Very impressive results. I have a question. You mentioned that masking needs to be refreshed quite frequently. What would be the most complex operation that can be achieved between two refresh operations?
Yeah. So, what is the most complex? I mean, it just breaks the proof immediately. So there's that. So, so the deprobing proof doesn't quite hold. In practical terms, yeah, it's a little bit gray area. I mean, for example, threshold implementations don't technically refresh. It's just like recycling the randomness from the cipher itself. So yeah, it depends on what you are doing. But if we play by the rules of masking, then we really should be refreshing every time. Because especially if it's like a secret key, if we let that lie somewhere, then and not randomize it, it's just a longer version of an unmasked key. It's like an expanded key in practice. So if we just get all of the bits of those masks, you know, we have the key. So I don't have a concrete answer to that because it's such a...
I understand. And do you consider your implementations to be first order protected? And if so, you know, do you consider the higher order attacks, you know, still, you know, possible, practical?
I mean, for this particular gadget here, we are kind of limited by the K-chuck permutation here. Right, we could technically increase it, but as you know, on practical terms, there's it's a continuous development cycle. So there's like a red teaming effort, finding attacks, and then we actually use some much cheaper countermeasures, randomized delays, whatever, in order to deal with those particular attacks sometimes. Right, it's a combination. Sometimes you can do like 1.5 order masking. And there's a fantastic new PQC signature scheme called WrapQ, which goes all the way to 31st order because it's designed that way. So it's not limited by, actually what limits dilithium to first order is quite often the K-chuck. So you can do a very similar signature scheme without that limitation and go much higher.
Thanks a lot.
Cheers.
No more question this time. I'll be very careful. Okay, so I think we can thank the speaker again.